Okay, we're back and we're going to solve or talk about the solution to that last problem I gave you, and then actually sort of extend these ideas a little bit, explore these ideas a little bit. The question says if any more than 0 switches are closed, if any more than 0 switches are flipped to their on position, essentially the LED should light. And I didn't say this explicitly, but that means 1 or 2 or 3. If any more than 0 are closed, it should go on. So I perhaps gave you a bit of a clue in the way that I drew these things, in the way that I drew the arrangement of switches, and I put the LED off to the side. This is the first time we're actually going to build a node. So I'm going to start by building something rather simple. I'm going to put power into this switch. Out of the tail end of this switch, I'll go into that LED, and out of the tail end of the LED into ground. So I have definitely not solved the challenge. It is true that if you close this switch, the LED will turn on, but the other two switches bear no relationship whatsoever. They can be closed or open, it doesn't care, because they're not attached to anything. So naturally, this is not the answer. We need to attach the other switches, and we'll do it one at a time, so that they also participate in this circuit. Now, the way we attached switches before was like switch over here, etc. But we need a different behavior. What we're going to do this time is I'm going to, oops, should not have drawn a dot there. I was thinking ahead. I'm going to attach this switch up here. Now that is a node. I don't want you to confuse it with the little poles, the terminals of the switch where it opens and closes. It's a node, meaning this wire is connected to this wire. Okay, so where might this end of the switch be connected? Well, if we connect it back up to that same place, if we connect two legs of the switch to any one place in the circuit, it doesn't do anything, so that's not the right answer. This leg of the switch, what if I connect this leg like that? Well, let's look at the flow. If this switch is open and this switch is open, the power comes through here, and for the first time that we've seen, it reaches a fork in the road. Power reaches a place where it can go what looks like straight or right here. Well, I'll just call it left or right. Of course, the directions don't matter so much. Power reaches a fork, and some of the power goes up this way and says, maybe I can flow here. And some of the power goes down this way and says, maybe I can flow here. Well, in this case, the power cannot flow through either of those paths because both the switches are open. But imagine the bottom switch were closed. Well, then the power would have, through this dotted line, a complete path power through that switch back up to here, and then all the way through the LED back down to ground. So we have built a circuit involving two of the switches, but not the third. Where's the third one going to go? We're going to sort of bolt it on top, just like we did the second. I'm going to put one leg of it over here, and I'm going to put the other leg of it over here. So now there's another possible path for the power to follow. The power gets here, and it could go through there, if this switch were closed, to there, to there. This is topologically equivalent to, it is a valid answer to the problem. But it is actually a little bit confusing to draw it this way, because you see all these nodes, there's 4 nodes drawn, and like what's connected to what? Well, first of all, something I want to be clear about, 5 volts, because of these nodes and the way they're arranged, 5 volts is connected to this and this and this. All of those are also connected to each other. They're connected through this common network of wires. So anything that is connected to another wire, they're all the way connected. So this is directly connected to this, even though it's kind of through this little path. But this is a slightly more confusing than necessary way of drawing it. So I'm going to redraw a circuit, but this is a correct answer. I'm going to draw an equivalent circuit that is just clearer, just easier to read. 5 volts on the left, and I'm going to draw a node there with 3 wires coming out. Now, I don't need to draw a dot here because it's just a turn in a wire, and you don't need to draw a dot merely when a wire turns. You only need to draw it when they connect. Now, each of these is going to get a little switch drawn on it. Aha, what's going to happen at the right side of the switch is another node, power comes out, goes through the LED, down to ground. This is the equivalent to this circuit. These two are the same. Which one is clearer to read? I believe this one is quite a bit clearer to read because there's two nodes instead of 4 drawn, but they are equivalent electrically. So if somebody handed you this schematic and somebody handed you this schematic, you could build the same thing like in real life from either schematic. So we've seen this interesting structure that we hadn't seen before. This is a structure, and this structure, like this, is a different sort of structure. There are labels for these structures, which we're now going to talk about. Not a great photon. That photon took a funny turn. If things are arranged like this, these are said to be parallel switches. In this case, they are parallel switches because the switches are the things that I have paralleled. If they are arranged like this, head to tail, these are said to be serial, S-E-R-I-A-L, not like the breakfast food, switches. And I want to point something out that's kind of an interesting property of these two different arrangements. In this case, if this switch or this switch or this switch is closed, the light will go on. In this case, if this switch, this switch is closed, the light will go on. Please fill in the in your mind. I'll pause for a moment. If this switch, this switch is closed, the LED goes on. Well, the answer here is if this switch and this switch, if they are both closed, the LED will turn on. And looking up here, if this one or this one or this one are closed, the LED will turn on. These are actually fundamental representations of the idea of and of the idea of or, logical ideas that underlie a huge universe of computing and computational thinking. So that's pretty interesting, just to consider that some sort of logic can be built right into a circuit. Now, by the way, this is an OR. We would call it a three input OR. You could build a 2-input OR that would look like this, drawing it in a kind of funny order. That's a 2-input OR as compared to a 2-input AND. You could also imagine having a 3-input AND. That would mean it would be a switch, then another switch. So you could start to think about the possibilities. If you wanted to make some sort of machine that would make some kind of simple decision, you could label these two buttons, this and this, and you could label these buttons, make some other machine that would make some simple decision for you. What else could be series or parallel? Well, it's not only switches. We could also have a circuit that looks like this. We could have a switch, just a single switch. We could have an LED followed by another LED. In this case, the LEDs are serial. Similarly, we could have a circuit. We could have a switch, don't need a switch, doesn't matter. We could have two LEDs. And in this case, those two LEDs are said to be in parallel. But wait, there's more. Instead of LEDs, we could have batteries that are in series and parallel. So just as an example, well, I don't need to draw that. You can imagine what series batteries and parallel batteries would look like. And finally, in case there wasn't enough interesting stuff going on, the the last thing I want you to think about that's very, very cool, consider a circuit like this. For instance, just as a very first step. Well, we can combine multiple structures together. And in fact, any place you see a wire, so let's say this little dotted line, I see a wire there, we could insert a circuit into that place, a sort of a little sub-circuit. So I see this little dotted line wire. I could imagine erasing that little dotted line, and I could zoom in and I'll put a big version of it down here. It could look like this. It could have like a three-way parallel OR sort of circuit inside of that little place, right? So you can think about all this world of possibilities. Circuits can be put inside of circuits, inside of circuits, inside of circuits. You can nest these infinitely. You can stack and nest and combine in all sorts of interesting ways and start to build really interesting complex circuits using only wires and switches and LEDs. Next, we're actually going to talk about the underlying principles of electrical flow and understand them in a more fundamental way so that we can do a little bit of mathematics necessary to understand what's actually going on quantitatively in circuits like these and others.